So let's imagine then, remember before we did a weak calculation where we talked about 1 gram of sodium chloride. We worked out the amount of sodium chloride there was in 1 gram. Well, let's imagine now that we're going to take our 1 gram of sodium chloride and we're going to dissolve it in 1 litre of water. So this might be what you would do to cook your potatoes for tea tonight, although you probably shouldn't put a gram of salt in, that's probably a lot. But that sort of idea, yeah? The sodium chloride is going to be the solute, because it's the thing that is dissolved. And the water is going to be the solvent, because it's the stuff that the salt dissolves in. And so if we want to calculate the concentration of that sodium chloride solution, we're going to use this little formula here. So the concentration, C, is equal to the amount of solute divided by the volume of solvent. Okay, so C equals N over V. And again, this is one of these little formulas that you could put in a triangle if you wanted. Because again, it's important that however you do it, you're very relaxed about rearranging this equation. So C equals N over V. V equals N over C. Amount equals concentration times volume. Being able to rearrange this to make each of those different things the subject of the equation, because all of those different forms are going to be useful in different types of calculations. Yeah? And so here we are. Our concentration of our sodium chloride solution will be the amount of sodium chloride over the volume of water in this particular case. We worked out earlier that the amount of sodium chloride that there is in 1 gram of sodium chloride is 0.017 moles. And we've got our volume of our water from the question, that's 1 litre. And so our concentration is just going to be 0.017 moles per litre. The volume that you put into this calculation must always be in litres. And oftentimes, because the glassware that you use in the lab is not measured out with markings in litres but in millilitres, we will give you volumes in these questions that are in millilitres or mils. Yeah? And so you have to remember to change the mils to litres before you do this calculation. Concentrations are always in moles per litre, not moles per mil. Okay, here's another one. Calculate the concentration of a solution formed when 0.23 moles of potassium bromide is dissolved in 250 millilitres of water. Potassium bromide divided by the volume of water in litres. So you can't put in 250 there, you have to put 0.25. You have to be okay with converting millilitres to litres, just like converting grams to kilograms. Yeah? And so in this case, the concentration will be 0.92 moles per litre. Yeah? So calculate the concentration of a solution prepared by dissolving 6.5 grams of sugar in 120 mils of water, given that the chemical formula for sugar is C6H12O6. Yeah? And so you're going to do that just like we've been doing. It'll be 6 times the molar mass of carbon and 12 times the molar mass of hydrogen and 6 times the molar mass of oxygen. And so if you work all that out, then hopefully you ended up with 180 grams per mole. See how I've set this out in steps. I mean, this is what I'm saying about the working. I mean, you don't have to say step 1, step 2, but you should be sort of thinking about setting it out in this sort of logical way. So if you got this bit right, but then the rest was wrong, then we can at least give you marks for this bit, because this was right. Yeah. So that's the molar mass. Then we work out the amount of sugar in moles. That corresponds to a 6.5 gram sample of sugar. So it's just the mass divided by the molar mass that you've just worked out to work out that it's 0.036 moles of sugar. And then in the third step, you would take that amount and you would divide it by the volume of water in your solution in litres. Okay, I think the last bit for today is looking at something called limiting reactants, or sometimes called limiting reagents, even though reagent is kind of an old-fashioned word. You still see it here used in this context, but limiting reactants. And so what we want to do is we want to take a few steps back to this business about balanced chemical equations that we talked about end of yesterday and the start of today. And we want to talk about these stoichiometric coefficients. Remember, the stoichiometric coefficients tell us the ratios in which the reactants react in a chemical reaction, right? So like for this one up on the purple here, nickel plus a half O2 gives one lot of NiO. We say that one nickel, a certain amount of nickel will react with half that amount of oxygen, right? That's what the stoichiometric coefficients tell us. But what you're going to find is that in almost all cases, when you go about doing a chemical reaction, the reactants that you add into the reaction, you will not be doing that in their exact stoichiometric ratios. Right? I mean, you can do that if you want, and you know, if you want to work out and do it accurately, but normally the reactants won't be there in that exact ratio. And if that's the case, then we have to proceed with this limiting reactant sort of a problem, because we have to work out which is the so-called limiting reactant. Just while you're writing this down, and because I've got time to waffle, yesterday we talked about this business about blowing up hydrogen balloons, and there was a picture in the paper the other day I was saying about how we have these kids burning these hydrogen bubbles on their hands. You may have seen pictures of the Hindenburg, yeah, the Zeppelin that blew up in New York back in the 20s. I'm kind of making that up, but let's go with it. It was in the States somewhere. And so these pictures, you know, this big airship thing that was full of hydrogen, and it caught fire, and people died, and there's movie footage of it. It's all very exciting. I suppose it wasn't if you were there, but anyway. One of the things about that is that even though if you have a balloon full of hydrogen and you put a match to it, like in here, if we did it in here, that balloon would explode. In fact, in the case of the Hindenburg, it didn't explode, it burnt. And the reason why it burnt was because there just wasn't physically enough oxygen in the air around the balloon for the stoichiometry to be met the way that it needed to be to get the complete reaction. Right? If you want the balloon to explode, you need to have half as much oxygen as there is hydrogen in the balloon. Now, we did that equation yesterday. It's a 2-to-1 ratio. And there just wasn't that much oxygen there. And so it didn't explode as such, it just burnt. It was still pretty bad, but that was because the two reactants, the hydrogen and the oxygen, weren't present in their stoichiometric ratios. Yeah? Okay. So let's look at this equation. This is a little bit more complicated than what we've seen so far, but something you may have done. Calcium carbonate, which is, what is it, quartz, limestone and chalk, I got taught at school, reacting with hydrochloric acid, HCl, to give CO2 gas and H2O gas, H2O liquid, and CaCl2AQ. Now this little brackets AQ we haven't met before. This is a way of symbolizing a thing dissolved in water. So the AQ stands for aqueous, if you haven't met that before. So if we write an S after CaCO3, that means it's a solid. If we write AQ after the HCl, that means HCl in water. And then you've got CO2 gas. The G in brackets we saw yesterday, that means a gas. The L after the water means a liquid. And then you've got aqueous calcium chloride. So again, calcium chloride dissolved in water. Right? So let's imagine we have a particular reaction where we have 3 moles of calcium carbonate and we react that with 7 moles of HCl. Now if we do that, then our 1-to-2 ratio required by the balanced chemical equation is not met. Our balanced chemical equation says that 1 lot of calcium carbonate reacts with 2 lots of HCl. But what we've got here is 3 lots of calcium carbonate and 7 lots of HCl, right? So it's not in that ratio. 3 to 7 is not the same as 1 to 2. And so instead what we have here is a situation where one of the reactants is called the limiting reactant and the other reactant is said to be in excess. And so in this particular example, we would say that the calcium carbonate is the limiting reactant because there's not enough calcium carbonate there for all of the hydrochloric acid to react. And so the way to work through this, which isn't on the slide, but we'll do on the board because we've got time. So calcium carbonate plus 2 lots of HCl the problem says that we've got 3 moles of calcium carbonate, right? If we want all 3 moles of the calcium carbonate to react, what amount of HCl do we need? 6. Yeah, we're happy with that? Because it's a 1 to 2 ratio. So if we've got 3 moles of that and we want all that to react, we need 6 moles of this. Yeah? The question also says that we have 7 moles of HCl. If we want all the HCl to react, what amount of calcium carbonate do we need? 3.5 moles. 3.5? Yeah. So if this is one of these things where you can't look at it and it just instantly appears in your brain how the answer is, I would suggest you do this sort of thing and then you look at these numbers and see which makes sense, right? If you want 3 moles of calcium carbonate to react, you need 6 moles of acid. Do you have that much acid in the problem at hand? Yes or no? Yes. Yes. Yeah? You've got 7 moles. You've got more than that, right? So you've got more than enough acid to react with this amount of calcium carbonate. If you want all the acid to react, you need this amount of calcium carbonate. Do you have that much? No, right? So there isn't enough calcium carbonate for all the acid to react. So the thing that limits how far the reaction goes until things run out is the calcium carbonate, right? So are we happy then that we've got enough acid to use up all the calcium carbonate, but we don't have enough calcium carbonate to use up all the acid? Yeah? So that means in this case we would say that calcium carbonate is the limiting reactant. It's the thing that limits how many product molecules we can make, right? Because what's going to happen is you're going to mix this with this, and the reaction is going to happen, react, products, and it's going to keep going until the calcium carbonate runs out. And then the reaction will stop because there's no more calcium carbonate, so there's no more reactant. And when it stops, you will have some hydrochloric acid left over. Yeah? And so we would say that the calcium carbonate is the limiting reactant, and we would say that the acid is in excess because you have more acid than you need to do the reaction, and so there'll be some left over at the end. Yeah? I'm hoping that there will be problems on that too. Limiting reactant, generally what you will find is this. If we give you a problem where we tell you about the masses or concentrations, if you like, of more than one reactant, you will have to do this sort of analysis to work out how, because the question will say, if you mix so much of this with so much of this, how much product can you make? In order to work out how much product you can make, you will first of all have to work out which of the reactants is the limiting reactant, because in this case, if you then wanted to work out, say, the amount of calcium chloride that you can get, you have to do that based on the amount of the limiting reactant. You can't do it based on the amount of HCl you've got in initially, because not all the HCl is going to react, because it's the thing that's in excess. Yeah? The reaction will go until the limiting reactant stops, and so the amounts of the products that you get, you have to work out from the amount of the limiting reactant that is present. Does that make sense? Right? So in this case, what amount of H2O do we make when the reaction stops? Who says 1 mole? Hands. Who says 2 moles? Who says 3 moles? A few hesitant hands. Who says 4? Who doesn't know? Well, who doesn't care anymore? Where's my statement? If we're saying that the calcium carbonate is the limiting reactant, then 3 moles of this reacts with 6 moles of this, and then the reaction stops because the calcium carbonate runs out. Yeah? So if 3 moles of that react, what amount of this do we make? Because the ratio is 1 to 1. Yeah? One of these reacts and makes one of those. When the reaction stops, we're going to also make 3 moles of this because it's 1 to 1, and we're going to make 3 moles of this, right? And we're going to have 1 mole of this left over. Yeah? So you have to work out first what the limiting reactant is, and then you can work out the amounts of the different products that you can make in the reaction, right? So if we give you a problem and it involves giving you information about more than one reactant, you will have to do this sort of thing first. Oftentimes we will say 3 moles of calcium carbonate reacted with excess acid, and then you're sweet. You know that calcium carbonate's limiting reactant, and you can just press on. But if we give you information about more than one reactant, you will normally have to do this first before you can work out the amounts of products that are formed.